qualche modo. Okay, I think we can start. The speaker of today is Moreno Ambrosin of the computer science branch of this school, which last year was him. Yes. Okay, as I already said other times, the presence of computer science can be a good complement, as long as it lasted, to our doctoral school for basically two reasons. The first one is that sometimes computer science is just hidden mathematics or applied mathematics, and we saw this last year with at least 2 or 3 seminars. The second reason is that some computer science make quite a non-trivial use of mathematics, and in some ways where mathematics can have non-trivial use. In other ways, in ways that seem trivial unless you start thinking about some things that implementing things is not so straightforward as it seems, because there could be some unforeseen things, or in this case some external interferences or influence. The typical example is hackers. You can project something which mathematically stays well in its feet, but with some external intervention, everything falls apart, and sometimes things are critical in this way. Okay, so but it's time to make you speak. Now, the title is Secure and Scalable Management of the Internet of Things Deployments. The speaker is Moreno Ambrosin, who is working under the supervision of Professor Mauro Conti here. And I think you can start.
Thank you very much. So, I'm working with inside the Spritz group, which is the Security and Privacy Research Group, Professor Conti, and I'm finishing almost at the end of my PhD program. So that's why I put almost PhD, not yet PhD. And so let's start. So my talk will be about security. Secure and scalable management of IoT deployment. So we work on this is a series of works that we have done in collaboration with the Center of Advanced Security in Darmstadt, in the University of Darmstadt, and the Inter-Collaborative Security Research Group in Darmstadt. And this basically we work on managing deployments of IoT devices. So we have many new services that are based on IoT. And then these services based on connectivity, and then when we have connectivity, we have services. We need also to think about security. So that's what would be the outline of my presentation. I will give a brief context, introduction about what is IoT and so on, and then I will talk very briefly about what is IoT device management. And I will introduce you also the two contributions that we have made in these 3 years. One is for a protocol for secure software update distribution, and the other one is a protocol for the verification of a deployment, so of the integrity of a deployment. And the concept of integrity will be clear afterwards. And finally, of course, we'll conclude and tell you something about what we are currently doing and what is our future work. So basically, what is the Internet of Things? Internet of Things is a buzzword, and it's used to define many things. And that has many definitions, and there's not just only one. And I like this one, which is basically defines the IoT as a set of a network of physical objects. So it basically is the extension of you take an object, you put some technology inside, you give communication, and then you use it to sense and interact with the environment, or to collect data, or to act on the environment itself. And this is what, in my opinion, defines better the IoT. And this also gives from a business point of view, you can actually think of IoT as the integration of things, like your I don't know, the fridge or your toaster, into business solutions, where you will have like a smart fridge, or you will have like a smart microwave that can tell you when things are ready on your smartphone, for example. So that's basically what we can, how do we picture the IoT. It's correct to say that things are everywhere right now, and things in terms of course, IoT devices. They are used in many fields, like factory automation, vehicular networks, like inside vehicles, and so on. And according to some recent forecasts, they are expected to reach like 50 billion. So, and sometimes some other forecasts say 100 billions by 2020. So we are pretty close to reach this very huge amount of devices that are pretty everywhere. So, like some characteristic about IoT devices, they're often tiny, low cost, low power, and typically special purpose devices. So they are meant for a special purpose. For example, you can think that one device may be meant to sense the environment to measure pollution, temperature, and so on. Right. And so these are two use cases, very classic use cases. So an automotive system in itself, an IoT system, it's more like more an embedded system, but this is pretty close. So we have a car. It is itself a system with plenty of sensors inside that are interconnected. And another example is Industry 4.0, which is the new basically, is the new type of industry that is foreseen by industry people, and basically it comprises different smart services. You see, smart word is everywhere here. So you have smart grids, you have smart mobility, smart buildings. So everything that before was simple. It's like everything that is related to industry now becomes smart because it uses these IoT devices. And so, but here I'm a security guy, and we have to talk about security. So why security? So IoT is very promising, but it's also a security nightmare. So the first reason of this is that devices are in general quite easy to hack. And we had many recent examples. So, for example, that we had the largest denial of service attack on a part of the internet in the US that was generated by IoT devices. And this is actually the large presence, the pervasive presence of IoT devices itself that provides an unprecedentedly large attack surface. So we have a lot of devices that can be easily hackable. We have a large surface, basically. We have we give the attacker a lot of power. Security here is important because IoT deployments now are controlling critical environments. For example, one is smart grids, which is the new generation electrical systems, surveillance, factory automation, and so on. And because the IoT devices that we always carry every day, like heart rate monitoring and so on, they actually sense private information. So like my location, my own consumption, if you think about smart metering, so like in electricity metering that automatically measure the power consumption in the house, and then they report to a metering data management system. And then we had heart monitoring and so on. So in the first case, we have this IoT may represent a threat for safety critical systems. In the second case, this is represent a threat for the system and user privacy. So what is the IoT device management? That IoT device management deals with all these four main tasks. The first one is provisioning and authentication, and what this means is that provisioning authentication is we have a network of devices, you have a deployment of devices, which is basically a network of interconnected objects, and you have to take a new device and put it inside the new network. And this is basically what this provisioning is. And authentication is that you want to make sure that the device is a real device, so it has the right to stay inside the system. The second one is configuration and control. So we want to have an interaction with the device. It's more like a technological issue. And then you want to provide to be able to distribute commands, to give commands to the device to act accordingly. Another task is monitoring and diagnostics. So of course, if you have a deployment of device, you have a system of devices, you want to know what they are doing, right? And if they are acting correctly, or if there is any issue with their execution. And last but not least, there is software updates and maintenance. So software updates, you want to be able to update the software of these devices running on the system, and to correct bugs. So there might be a bug that may be even exploitable by an attacker, or you want to provide simplified new functionalities. And typically, this is carried out over the air. So you don't want you want to take the device, shut down the device, install the updates, and then turn on the device again. Because if you have billions of devices, you can imagine what would be the cost of doing this. But they typically do it over the air. Like when you receive, it's like when you magically receive the new software updates for your phone, and it says, "Oh, there's a new software update for Android." In a similar fashion. So what's the system model? So from now on, we will use this model as a reference to explain what we have done. So we have deployment of devices, which are heterogeneous and is potentially very large. And we have a management entity that needs to carry out all the management tasks, right? And given the potential very large scale of this deployment, this management entity will not do it like point to point, but we rely typically on an intermediate infrastructure. And typical examples are what are called content delivery networks, or even a new networking technology that has been proposed, like named data networking, or other trends like edge computing, which adds an additional layer between the cloud, which is basically, you can think this as a server, like a cloud server, and the device that needs to be managed. A content delivery network is so we use a daily content delivery network. So if, for example, if you browse Facebook. Facebook, for example, delivers large files such as pictures and videos through a content delivery network. So you're actually using this infrastructure, these structures every day. So they are basically an intermediate network that performs two important operations, which are data caching. So basically they cache data close to the devices. And what means caching? So they keep a local copy, so that subsequent requests are satisfied by a local copy here, so that if this device needs to ask something to this other one, it does not, the request doesn't go through up to here, but just is satisfied by these devices. So where the first time it's satisfied by this one, and then like local nodes here, they keep a copy of the data. And also aggregation, because if you want to collect statistics on the population, then what you don't really want to have, for example, you want to collect some average temperature. You don't really want to collect all the temperature measurements and then compute the average, because it will be like too computationally expensive. So what you do typically is you rely on this intermediate network to perform some type of aggregation, and also to aggregate requests. So like requests for the same thing are aggregated, so only one request is propagated up to the device. And when you talk about security, you typically consider an adversary model. So the adversary model describes what are the capabilities of an attacker and what the attacker is interested in doing. Okay. So in our case, we consider this the management entity as trusted. So we trust everything that comes from this source, and we trust him to this source, the management entity, to do the correct operation. So he doesn't want to harm anything or anyone. Then the threat can come from either the intermediate network or the end devices. So what does it mean? So we assume in particular that an attacker can actually take control of part of or all this network, with the intent of compromising the integrity, authenticity, and confidentiality of the data. And this means that he may be interested in trying to access what these two devices are transmitting. So for example, he's requesting some software updates from this device, and the updates can be confidential, can be proprietary software, and this node may try to get this software update. Okay. Or he may want to replace content that is transferred from this node to these devices by being in the middle, like to perform what is called a man-in-the-middle attack, like trying to take this data and modify, replace them, and then let the device think, oh, this is a new software update, instead it's something else, right? Like malware. Another threat can be like device integrity can be compromised. So an attacker can take the device and can replace the software inside to perform some malicious operation. An example is we are sensing the temperature for some critical purpose, and an attacker can simply take the device, replace the firmware, and always replace with, oh, everything is fine, the temperature is okay, while it's not. And so this is a typical example of what an attacker can do if he can replace, he can violate the integrity of the device. But this will be clear later on. So these are mainly two contributions that we are going to talk about. This is more like future work. So the first one, we design a protocol to distribute software updates. And the second one would be is a protocol to perform this verification to get some aggregate value that is representative of the integrity status of the devices of a large population or large deployment. And this is mainly a future work. We are currently working on providing a framework for common distribution and statistics collection from devices in the same adversarial setting, this one, as before. So let me start with software updates. So as I mentioned before, software update distribution is important. Why? First, from a pure business perspective, we may want to provide a new functionality to a device and to only people that are subscribed to some special service. So like if you think about the GPS, you want to provide the maps updates only to people that paid for them with some additional information, and this is an example. From a security perspective, you want to minimize what is called a window of exposure. So windows of exposure is the time that it incurs from the time a vulnerability has been introduced. A vulnerability can be simply a bug in a code, and until when the patch is delivered and installed in the device. So this is actually the time it takes, the time within an attacker can actually carry out some malicious stuff with exploiting the vulnerability. What I mean by vulnerability, so there are some vulnerabilities that are called, for example, there is a buffer overflow. When an attacker can simply act in such a way that the code that is running on the device writes out of a buffer and then start writing in areas of the memory where it was not supposed to write. In this way, the adversary can actually make the device run arbitrary code. And this is basically a vulnerability. And typically, this is patched with software updates. So a software update distribution system can act in this direction, in this area here, marked as red. So we want to minimize the time it takes from the patch to be released and the patch to be installed. So this all have to do mainly with the distribution of the software. So these are the requirements we identified for secure software update distribution system for these deployments, and this is first of all is fast delivery, of course. Updates has to be confidential, so there may be the need to keep that software update confidential. And we want to maintain, of course, authenticity and integrity. So a device must be able to verify the authenticity of updates that is downloading, and its integrity, so that no one modified the update on the fly. So basically, they did not perform a man-in-the-middle attack. But at the same time, when we are talking about software distribution on large scale, we want the device to be able to verify the freshness of the updates. What do I mean by freshness? We want to verify that the software update that is retrieved by the device is still a valid one, is not expired. So maybe there can be a new one, but let's say that the device just retrieved an old version of the software, but a new one is available. And last, we want to maintain this distribution cheap and that can be leverage existing infrastructure and any arbitrary caching and aggregation infrastructure like content delivery network or any other intermediate infrastructure. And to this end, we actually design a protocol which is called the Update Indicator, which is a protocol that is able to satisfy all the requirements before, and that can leverage intermediate potentially untrusted caches or intermediate distribution networks. And this protocol is designed on top of using a new cryptographic tool that has been recently proposed, which is called ciphertext policy address-based encryption. That we'll explain a bit more in the next slide. It's not our contribution, this is actually not our contribution, but this is something that we use as a building block to build our protocol. So our contribution per se is the protocol, and we actually describe this and on top of data networking, which is it's not really it's a protocol for that is for data-oriented distribution of data. So it's that data-centric network protocol. So it's a new protocol that's been proposed to try to replace IP and to overcome some of its drawbacks. To speed up content distribution anyway. So it's not really, I mean, this is just informative. It's not, I'm not going to tell you something about this because for space and time reasons. But instead I will just introduce you how CPAB works. I will not talk about how you can construct mathematically this, because the constructions, there are different ways to do that, and all of them has pros and cons. I will just give you a very high-level idea of what you can do and how this works in practice and why this is important for the practice. So ciphertext policy attribute-based encryption is a public key scheme. It's a public key scheme where we have that allows a data owner to enforce access policies like Boolean access policy on data. And so this is the way it works. So you have a trusted authority which generates keys. And it generates private keys for users, and each private key is associated with a set of attributes. So these attributes reflects the key and the owner, basically. So if you think about devices, so this private key may represent like devices of a certain series and like some specific model of device. Okay. As all the public key schemes, we have a public key, which is public by definition. And what Bob can do with this key is he can take some data and encrypt them, applying an access policy on top of it. So he can express this as a Boolean access policy, and say that I want to encrypt this data so that only who has these specific attributes or who has attributes that satisfy this policy can decrypt it. So this is what you can do with this tool. So, and the access policy in this case goes with the data. So you don't need anyone else to enforce the access policy. So the access policy is enforced cryptographically. So then you can, so Alice, when it receives this encrypted data, it can actually decrypt it with this secret key, if and only if the attributes associated with the private key satisfy this policy. So that's very simple, but actually this is a very powerful tool, especially if you want to perform access control on data, you want to perform large-scale distribution, and you really don't want to target, you don't want to perform like point-to-point encryption on data, but you just want to encrypt data based on some characteristics of the decryptor. So this is a system model again. Is slightly different from the one I showed you before, because in this case we are considering 3 entities. This can be also, they can run all in the same machine, but they can also run on 3 different machines. And we have a distribution server, which is in charge of distributing the software updates. We have a policy server who actually defines what are the access policy on the data. And we have finally an update server, which is an entity that distributes the information about the updates. So when he has the information about, oh, a new update is available and so on. So the protocol works in 3 phases. The first one is called update publication, and this is a required pre-processing to be able to securely distribute the update. The second one is update selection, where we have devices that try to poll for updates. So you don't actually really want to push updates down to the devices, but you want to let devices themselves randomly wake up and say, oh, is there any new update? So the reason why is that, especially for IoT, that you have also, they are low cost and low power, and they're typically battery operated. So basically when you want to save energy, so the devices, they have sleep periods where they sleep to save energy, and they randomly wake up and just ask for software updates. So typically like a polling mechanism is preferred when you have to deal with software updates. And the final phase is update retrieval. So when you actually, the devices here in this session, in this phase, they just retrieve information and they know if there are any software update available. in the last part, they directly download the update. So here is the first phase, how it works. So when the new software update is released, then the policy server just generates a random symmetric key and encrypts the update with this key. Then what it does is sends it derives an ID, a unique identifier for the software update, typically a hash of the update, an access policy for this, and a set of attributes that can satisfy this, a set of combinations of attributes that can satisfy this policy. So in a deployment, you will have like a finite number, and not so big, large in practical settings, large number of combinations of attributes that can actually are entitled to access these software updates. So you actually all pass all this information to the update server, who performs the actual encryption with attribute-based encryption. So actually it enforces the access policy on what? On the key, symmetric key. And this is done because we don't know in advance the size of this update, and typically symmetric encryption is much more efficient, and typically public key schemes are used on symmetric keys for computational reasons. After that, then this information is published. And this information contains the encrypted symmetric key, the ID of the update, which is the hash of the payload of the update, of the binary, a timestamp, and a validity period, which determines the validity, how long this update will be valid. And this actually is signed. So this symbol is meant in this picture means that this information is signed. So like this update server puts a signature on top of it, like a digital signature. On the other hand, we have the encrypted package is given to the distribution server, who actually publishes simply under this ID. So basically, this update is associated with this ID, and the information about the software update is distributed here, while the update itself is distributed in a separate way. The update selection is the phase where devices query for information regarding the availability of new updates. So assume that we have two types of devices here. This is the intermediate network. We have the update server, and they basically request data to they request, oh, is there any update available here? So they will get this information. And these information are freely distributed to anyone asking, so there's no access control performed by the update server, because there is no need actually, because this key is encrypted with already has the access policy in it. And so if they are entitled to receive this information, they will just decrypt the packet, because they have a private key that can do that. Otherwise, they will just won't be able to access the content, right? So the intermediate network will cache this information, so when subsequent requests will come, they will be served directly by this intermediate network, of course, because they're making some sort of caching. And the delta t, so the time that is information that is reported in the packet is required to let the devices check whether this is like something new or not. So they have an idea of, this gives an idea of if the content is too old, or if, for example, intentionally, one of these nodes maliciously is trying to give some old data to prevent this device from updating, for example, to perform an update. The third part I did not report here because it's simply requesting the same. It's very similar to this one, so it's just devices request the software updates, and then it gets delivered by this time the distribution server, and the update is cached inside the network. And the devices in the end, if they were able to decrypt this, they actually will be able to decrypt also and to access the software update and finally install it. So to try to have an idea if this what's the performance of this, we did two types of evaluation. So first of all, we tried to do a large scale simulation using the network simulator, which is called NS3. It's a very popular one, and using also a plugin for it, which is called direct code execution. And direct code execution allows to run real code
on top of the network simulator. So like be a network code, like a real HTTP server and so on, and not just simulating it. We use this topology as a reference. This is actually, has the same structure of popular backbone network in Germany, and it has been used in many other related works. And we measure what's the difference to what is the performance gain in terms of time it takes. Remember that we wanted to reduce the window of exposure. Time it takes to retrieve a content, but also like a software updates, but also for the software update distributor, what is actually the cost in terms of traffic and request that is going to receive. So we made all these devices. So we attached devices here. I don't think it's really visible, but here there are some gray robots here. So we attached like from 100 to 900 clients here. Okay. And form this, yellow triangles represent the untrusted intermediate network, and we attach the software distributor here. So we perform like many simulations, and this is actually a summary of what we measure. So here is the graph is in log scale. This is the data which is transmitted by the updates server. This measures the traffic, and this measures the time. So this is from an update server point of view. This is what, like update system point of view. This is the amount of traffic that is sent and received. Okay, this is in terms of request, of course. This is in terms of data that is actually pushed out. This actually I put here when you see NDN. This is because we use the NDN protocol to do this test, and this actually what this is the amount of data using our solution, using update indicator, and this is typically providing a distribution like HTTPS. So when you actually you take a request for each, so the distribution server receives a request and then responds point to point. So you create multiple encrypted channels to distribute these updates. And this is actually the second result. So here, this is the runtime. So as you can see, the runtime grows very quickly, and these are seconds. And while we were able to see, like, this is actually a logarithmic growth, but this is not visible because it's very small. So this is actually the results we get. So we know that we were, this is actually a cryptographic scheme on the low resource constrained devices. And so the reason is that typically the more complex is the crypto algorithm, the more expensive it is in terms of computation, in terms of operations. In particular, like the existing implementation of CPLB are based on pairings, and this is known to be computation expensive. And still the feasibility of doing this type of cryptography on our resource-constrained devices is still under examination. So what we have done here is, starting with some results that said that this is actually a type of cryptography was unfeasible on smartphone devices, we try to implement the algorithm by ourselves using in C language and cross-compiled for Android devices, and we were able actually to show that to improve the performance with respect to the previous one, and to show that indeed this type of cryptography is feasible up to some extent. So that the complexity in terms of also performance of CPLB varies in terms of number of attributes that you use and the size of the access policy. So the bigger the access policy, the more complex and computationally expensive would be the computation. And so we did like a practical evaluation and see that this is actually indeed feasible. And we did even more. We tried this code on top of more IoT-ish devices than a smartphone. Our smartphone is more like a general purpose computing. So we tested those on popular boards that are used in IoT development. And we were actually provided some sort of framework to be able to have an initial assessment of what would be the cost of using this cryptographic tool on these devices. So these are two results that we recently published, also out of the work on software update distribution. So that's basically all for for the part of software update distribution. And then the second contribution we have made is about the very fine is the integrity deployment of IoT devices. And by integrity, I mean performing what is called a remote attestation. So a remote attestation is an interactive protocol between a prover and a verifier that allows the verifier to measure some property on the prover in a trusted way. So basically, assume you are a verifier and you want to know if a certain device, like that video camera there, is actually running the correct code. And by a correct code, correct software, sorry. And by correct software, I mean like the firmware that was installed at the very beginning. So I want to make sure that no one actually modified the code that is running and the software that is running on that video camera. So I can use, so provided that I have some trusted component inside this device, and many devices, also your laptop probably is running one of these, is a hardware component. It's called Trusted Platform Module, which is very popular. Also my laptop is, the common laptop is developed with these low-cost devices. Provided you have what is called in general root of trust for measurement, you can actually perform this type of interactive protocol. That works more or less as follows. You have a verifier and a prover. The verifier sends a challenge, a random challenge to this prover. The prover performs measurements of the software or like parts of the software. So it can take, this typically translates into computing a hash of the software, and then compute a digest, and then signs this digest with some secret, shared secret key, which is a key shared between the prover and the verifier. And the key stays inside the trusted component, of course, because this is a requirement. I mean, the software, the malicious software, potential malicious software cannot access this key, otherwise this would not work. So the device, the prover computes this message authentication code to prove that, okay, I did some measurement, I did this measurement, and then I prove you that I did this measurement. So this proof. And then finally, the verifier computes the same message authentication code on an expected configuration, on expected measurement H prime. So a verifier already has to have an idea, a priori idea of what is the expected software. So I know that this video camera is running software XYZ. So what I can do, I can run an attestation with that camera. So I can pre-compute this H prime, and then let the camera and the trusted component inside the camera performing the same, and then I can simply compare the two message authentication code. So this is actually a well-established technique to perform this type of check, and works on a software-only attacker. So we are assuming that we have this root of trust for measurement that cannot be modified by an attacker. Otherwise, the whole procedure will not work. This actually used in practice. There are also many devices are able to do that. Also Linux operating system, and also Windows 10 is providing support for TPM, and it's trusted platform module. This trusted computing, which is the whole research area here. Anyway, so the requirements, the basic requirement to perform this to do this remote attestation is that the code that actually is doing the measurement should run uninterruptedly, of course, because an attacker should not be able to interrupt the execution of this measurement. Otherwise, it could simply stop the measurement, do whatever it likes, and then it replace and go back to the previous version, and then let the measurement run again. And so the measurement, like the root of trust for measurement, will never be able to know what's going on in the device. This should be running on an isolated environment, and also should have some shared secret with the verifier. Okay, this is again, this is a very well-established technique. And there's nothing that it actually works. Also, is used in practice. But so what we when we go back to the previous to our scenario where we have like a lot of devices, typically a verifier does not really want to perform this interactive protocol with every device here, because potentially we can have very large deployment. Right? So the problem here becomes, how can I do, like, I can perform a verification of the integrity of a whole network of devices efficiently. And to the question that we want to answer, are the devices running a correct software, or which of them is in an incorrect state, or is running an incorrect software, and so on. So performing it iteratively is too complex. It's close linearly with the number of devices, and this is not very convenient. So, so there has been a few works in the literature doing that, dealing with this problem, and the first one is called SEDA. And this work actually, what they were doing is they were considering a network of devices, and then they were organizing the network as a spanning tree, and try to perform this attestation, aggregating where each node of the spanning tree were attesting its children, its child nodes. So this is actually a first step, and actually this makes the complexity logarithmic in the number of devices, no more linear. So it's much better for scalability. But it has a cons. So this forces every node to be equipped with some root of trust for measurement, which is always not the case. I mean, if you're using some public caching infrastructure or like for general public infrastructure, that the device is not, I mean, provided that this device will run any root of trust for measurement. And then all the nodes needs to be, and for this reason, that all the nodes needs to participate to the attestation. Another drawback is that, of course, we are assuming a software-only attacker, but it might be the case if we go to a stronger attacker model, we may have an attacker that can also modify the hardware inside the device. So in that case, compromising one device will compromise all of them. That's not particularly good, but still is a very valid attempt, first attempt towards providing a complete solution for this. They actually try to further improve their solution in DARPA, which is another protocol that they proposed, and trying to extend it to provide some other features like peer absence verification. A drawback of this solution is that it requires full connectivity between all the devices, among all the devices. So what we have done is we try to say, okay, let's in our adversarial setting, where actually we have an aggregation network, which is general purpose and can be untrusted. So what can we do here? So these are our assumptions, and that the assumption is as a reduced set of assumptions, like more realistic assumption with respect to previous work, is that only end devices are equipped with some root of trust for some trusted hardware, some trusted component. And the aggregator nodes are organized in a tree structure and can be arbitrarily any type of device. So it can be a Raspberry Pi, can be a computer, can be a server, can be anything. These are some requirements. Of course, we want efficiency, scalability, and we want the protocol to be decentralized. We don't want to have like a centralized control of the whole protocol, and we want some degree of flexibility in the way this computation is performed. We don't want to have to work on very static networks, and we want this technique to be applicable to low-end devices also. And this actually also we want a better resilience to physical attacks, and in particular we want we have two requirements in mind. So if an aggregator gets compromised, we don't want to compromise the integrity of the attestation verification of the whole network. And we want to be able to, and if one device gets really hardware compromised, only that device should be compromised, not all of them. So that's the idea, like the attestation proof. I'm always talking about the attestation, of course, like the process. Because in previous work, if I were able to compromise one of the devices by hardware also, I could fake the verification of the whole network. So that's not very good for security. So we designed a protocol, which is called SANA, which stands for Secure Network Attestation. And basically the idea is that we broadcast a attestation request to all the devices, and then the devices perform an attestation response, and the attestation gets securely aggregated through the network. And the verifier only gets one single attestation proof that they can verify hopefully in a linear time. I say hopefully because in order to achieve this, we design a new aggregate scheme, aggregate signature scheme, which is called optimistic aggregate signature scheme, and it's called optimistic because it's based on a simple assumption, which is particular that we'll explain in a minute, and this it makes particular sense in our scenario where we want to perform this type of attestation. And it's actually work that was published in the CCS 2016 this year. And so, a few words on this signature scheme. Again, I'm not giving you details on the mathematical construction of this scheme. We combine basically two existing signature schemes and then provide a proof that in the paper that this actually is the new scheme is still secure under the same assumption as the other two signature schemes. So what is the? But I will simply briefly introduce what is the type of signature useful for, and then why this is good in our scenario. So it allows to aggregate a signature, a set of signature, into a single smaller one, and it assumes the existence of a most frequent message M. So basically, what it does is just you have many devices, and all of them need to have the private key, a different private key, and a different private and public key. Sorry. So what this aggregate signature scheme allows to do is to have each device can compute a signature on any message, and we are able to combine, to aggregate this signature into one single signature. But with some, and this actually is done to be able to reduce the space in the size of the signature itself, and to be able to reduce the time it takes to verify the signature. So because verifying one of these signatures, the idea is more efficient than verifying like any signature. Okay. So, sorry. So we assume in the scheme we assume the existence of a most frequent message, which is signed by most of the devices, and this allows us to improve the performance of the old signature scheme. And what we were able to achieve is that a signature size and the verification time, the time it takes to verify a signature, is linear in the number of signatures on messages that are different from the most frequent one. And it's optimistic also because it has constant performance, so the verification is constant when all the devices sign M. This may seem like a bit weird, but again, I mean, it will be more clear in the specific application. And the good thing is that it's dependent on in the number of signers in the network, but still only dependent on the number of signers, so the devices and the signature that are computed on messages that are different from this one. So the way it works is more or less as follows. It's simplified, and just to give you an idea of this works. So every device has its own private key, so there are different private keys, of course. So let's assume that this is the most frequent message, and this is another type of message. So when a device signs this type of message, then it produces a signature, alpha 1, and then there are all different signatures, of course. So alpha 1, alpha n. So this actually, so you can see that the result of this signature function is a signature value, alpha 1, and an empty set. Why an empty set? Because if you sign a different message which is different from M, then you have to report the small signature value, and you have to attach to the signature the public key that signed this message. So so you have to attach this. When you actually perform the aggregation of this signature, all these signatures get combined to just one signature value, we call tau here. And then all these sets are, there's a union of all these sets, basically. So all the public keys are attached. In the end, what you will get is you have one single value, tau, and you will get a beta, B, which is composed by the list of messages. So for each message, different from the most frequent one, you will have all the public keys that sign that message. So the verification of this signature is as follows. So you can actually, you take the signature, you take an aggregate public key, and an aggregate, so this is actually the signature value that is used by this verification. And you take what is an aggregate public key, which typically is the product of all the public keys, basically, minus the keys of the device that did not sign anything. So you assume you have a finite network of, or like a finite set of signers. like a limited set of signers. And then actually you take an aggregate public key, and then you basically take out all the nodes that did not participate. So the public key of the device that did not participate in the signatures, aggregate multi-signature scheme. And you also take out all the public keys of the device that signed the most frequent message, basically. So this is actually what is APKN. And in this way you are able, this actually has a complexity which is, and this and the verification, which I'm not showing you the details of the verification here. So the overall, we have a complexity which is linear in the number of devices that sign messages that are different from them. And this actually technically is still linear in the number of devices, right? But in practical settings, especially if you do attestation, then what you can assume is that most of your devices will run in one node correct state, right? Because if you have a deployment of devices that are all, most of them are running in an unpredictable way, that's actually not the efficiency of attestation is not really the biggest problem. And this actually, this assumption is very true in practice, but so there are ways to say that, to be sure that this actually is the verification is constant time, but these are the details are in the paper. So that's so this is actually how the aggregate, the optimistic aggregate signature works. And this is how we used in our attestation. So we have devices, they are equipped with this root of trust for measurements. The verified simply, it works as follows. So we have the verified distribution challenge. And then the challenge contains the set of allowed configurations for the devices. And then the hash of the concatenation of all these configurations. So typically a configuration is a hash. So basically here we're computing a hash of hashes, concatenated hashes. So we distribute these two things, plus a nonce, of course, because we don't want to protect ourselves against reply attacks. And then when they receive the challenge, what they do is they compute a signature, like an aggregate OAS signature, over over HG and N, concatenated with N, if and only if the device can actually assess that the device is running on a correct state. So in our case, the verification of the correctness is performed inside the device in the root of trust for measurement component. So if the device knows that this is in a correct state, it performs a signature on this. Otherwise, it simply performs a measurement and then computes a signature of that measurement here. So as you may imagine, this plus other things that are other details that I'm skipping here in this talk. So this part is the most frequent message of the whole network. So because we are assuming that no matter if the devices are heterogeneous, they will still compute a signature of this HG, which is a unique value is equal for all of them. Even if they have different configurations, this is equal because it's a hash of hashes, which is one single. So they will compute a signature of the same message, basically, if they are all the same. And then the messages are aggregated, as I showed you before, along the tree, until there is the verifier who is able to verify the signature in somewhat constant time. And if all of them are running a correct software, this will be constant time. And why this is good? Because we have reduced the need for these intermediate devices that aggregate this proof to be equipped with the same trusted hardware. So these can be arbitrary trusted device. And so we are able to detect and attempt to compromise this value. So assume that an attacker wanted to compromise one of these devices, and then one of these nodes to be able to say, so if the verifier wants to say, oh, is everything fine? Then he responds, yeah, everything is fine, even if he actually compromised this device. So this cannot be done, it can be detected, immediately detected. And also this is good because the software attackers on end device also can be detected, of course, because this is actually the way it works for. The way attestation is meant for. But this actually, of course, like hardware devices, hardware attack on these devices, which is a different attacker model, cannot be detected. Can actually fake the attestation, but they can actually not modify the attestation value of these other devices. So we did some implementation to verify the performance of our algorithm. So we provide a security proof in the paper, and basically we provide a proof of concept implementation on a resource constraint platform, which is based on Titan. Titan is a security architecture for IoT, which has been proposed in 2015. And it runs on, is meant for low-end devices, so devices that runs on 24 megahertz MCUs, for example. And we try to measure the performance of this signature algorithm on implementation, proof of concept implementation that we have made on these devices. And it takes more or less 2 seconds to compute a signature. So basically the whole attestation process is dominated by this signature, and it's more or less 2 seconds. So it has some overhead, but still is a manageable one, because you're not running this attestation request every second, but you're running, I don't know, like the number of times you're running a day depends on, of course, on the requirements of the application. Well, in our simulation, we did a simulation where we did the same benchmarks on higher-end devices to simulate aggregators, and in particular Raspberry Pis and Intel Galileo, which are all IoT boards, but are much more powerful than 24 megahertz. And when we perform a large-scale simulation using another network simulator, which is Omnet++, on up to 1 million devices, and with communication link that are configured to simulate Zigbee, which is a protocol that is used in IoT applications. So that's the results. We did a comparison with previous work, in particular with SEDA, because we were able to provide, which was the previous one I talked at the very beginning. We did some comparison, and this actually are the results. As you can see, the overhead, so that's the time it takes to perform a global attestation. So the verify simply broadcasts the challenge, and then takes the request gets aggregated, and actually the verifier actually can verify the attestation proof. So this is actually the time. This is the time it takes, and you can see, I mean, it takes only up to 12 seconds to be able to perform attestation of 1 million of devices, which is quite huge deployment. So it scales logarithmically. That's the main most interesting part. And actually, we did some comparison with the previous work, and we say that the performance is slightly worse. This actually was on a setting composed all of resource-constrained devices. This actually was a setting composed of slightly more powerful aggregators like Raspberry Pis and so on. And this actually, as you can see, we have slightly worse performance with much better security guarantees. And this performance are mainly due to the fact that the encryption that is used, like the signature scheme, is resource intensive for these devices which are resource constrained. So this to conclude. So management of IoT devices is important and has many implications for the security of a deployment. So you want to, when you have deployment, you want to manage it and you want to keep it secure, because security is important in many ways. I presented here 2 of our contributions, and one regarding the distribution of software updates, the other one on verification of integrity of a network. And in particular, these 2 works, Authenticator and Sana, I've shown you before. And we're still working on in this area. And what we have recently actually submitted work to the ICDCS conference. And the idea is that we want to provide a framework that allows devices to self-manage. So to be able to autonomously fetch commands, call for a command source for commands to execute. For example, now measure the temperature, now like move something or something like that, like change position and so on. And this actually we are working on this. We did an implementation of low resource constrained devices, and the idea is that we abstract the process management into an extended finite state machine, and then we translate this finite state machine into a set of requests that the device can have, of steps that the device has to perform in order to carry on its management life cycle. So that's all. So I'd like to So thank you very much for your attention, and thank you very much for listening to this talk. If you have any questions.
Okay. Questions? Well, I have one. It seems that can you come back one slide?
This one?
Or two? Then. Okay, so as far as I understood, the authenticator is secure, but not so scalable in the sense that you told that it has a linear complexity. Linear meant on the number of devices which need this update.
Well, it is linear. Technically, yes. The point is that if n devices need the same update, then the caching infrastructure, so typical content delivery network will provide some caching closer to the device, and they will keep a local copy of the content, and so like multiple requests in different regions of the same update, for example, different areas, right, that will be directly satisfied by this device. So by this intermediate caching infrastructure. So the idea was to take the system model, take this caching, provided that this caching exists, and provided that we don't want to give trust to this, so we don't want this to trust this intermediate infrastructure to be able to for integrity, confidentiality, and so on. So the idea was to try to find a compromise, the best compromise, to be able to still have all the security property we have in mind, but still maintain some logarithmically, like to have like a better scaling than linear, of course. So, yeah. So that was the idea. So basically, this is in the end the complexity is in the linear for the distribution server. So the server that is actually distributing the updates is linear in the number of possible configuration that exist in the network. So if you have like 1 million devices, you will have for sure a much smaller number of possible configuration of devices in practice, of course. I mean, theoretically you can have exponential number of them, but of course in practice, for practical deployment, all this work was meant as a very strong practical intent. So some of the results are still valid, of course, from a theoretical perspective, but are much more appreciated in a practical setting.
Okay. Other questions? Okay, then we can thank Moreno.